So for the arc length, what we're looking at is the distance traveled by a particle along its path. So remember, we defined arc length in the past as S, which equals the integral from A to B of 1 plus derivative squared dx. And so I'm going to rewrite it. We know this is also A over B, the square root of 1 plus dy dx squared dx. So what I want to do is I want to rewrite this using my definition for parametric equations. So I have 1 plus, and then I have dy dt over dx dt squared dx. And I can keep on rewriting that. I know that's the integral from A to B of the 1 plus, well, I'm going to get a common denominator actually. So I have dx dt squared plus dy dt squared, and all under the radical over dx dt squared, and that's times dx dt dt, because I'll get rid of the dx, right? That's the same as dx, okay? And remember, because if I dx dt times dt is just dx, so that's the integral from A to B of dx dt squared plus dy dt squared over dx dt, if I take the square root, times dx dt dt. These cancel out. So my new arc length is integral of dx dt squared plus dy dt squared dt, or integral, remember, that's f prime squared plus g prime squared, because remember, x equals f and y equals g dt. Remember, because x is f of t and y is g of t. That leads to a theorem. And the theorem is arc length in parametric form. So it says if a smooth curve C is given by x equals f of t and y equals g of t, such that, this is important, such that C does not intersect itself on the interval, sorry, A is less than or equal to T is less than or equal to B, except maybe at the endpoints. Then the arc length on the of that curve C on the interval is what we just said, integral from A to B of dx dt squared plus dy dt squared dt, or derivative of f squared plus the derivative of g squared dt.